Welcome back. We are on problem 5 for the ACM Programming Competition from Marquette. So for this one, it's called Circle the Wagons, and we are given 3 points, 3 XY double precision points, and we are told to find the center of the circle that those 3 points make up. Or in other words, this will be the circumscribed circle of those 3 points. So let's just take a look more at the problem in depth. So we have these 3 points over here. We'll come to the math a bit later, but we've got these 3 points. And the idea here to solve this is that we're going to have to draw a triangle in between each of these 3 points. And the circle that intersects those 3 points, the center of it is the intersection of the perpendicular bisectors of the sides of the triangle. So we have these 3 sides. If we pick any 2 and find the perpendicular bisectors, so those are the lines that are perpendicular to the segment and also halfway between the 2 points that make up that segment. So we just pick any 2 of them. In this case, we're going to use A and B and then A and C. The intersection of those 2, so this point right here, is the center of our circle. You can see that that's right about at the center. So we're going to have to come up with a plan to find this. So that was the main geometry of that. Just remember that from your geometry class. Now we're going to have to use some equations of the line to find this intersection point. So there's going to be quite a bit of algebra that we're going to have to implement in code, which is going to be the main challenge of this problem. So let's plan out what we're going to need. To start, I guess we can start up with the shell of our code. So let's just get a scanner to get our keyboard input. And the first line, as in the same with the other problems, is the number of test cases. So we can get that in with next int, KB. And we can use that same loop that we've been using for the other ones. So this loop will loop through each test case once. Alright, so we're going to be manipulating a lot of numbers, and we're going to need a good way to keep track of them. So we're going to need a coordinate class, or at least this will be a good implementation for it. The coordinate class will just be a container class for x and y pairs. So there's just going to be 2 different variables, x and y. And since this whole program has to be stored in one file for the competition, we're actually going to have to put this in an inner class to the Circle the Wagons class. So you can actually write classes right inside your other classes, just like this, and this will still be accessible to any code in the file. So for our coordinate, we're going to have an x and a y that we're just going to put in once in the constructor, and that'll be it. It'll just be a container. We can access those x's and y's when we need them. So we just have this constructor that sets them once, and then we can reference it just by doing .x and .y. Alright, so we'll be using these coordinates quite a bit throughout the problem. So let's just do the input right away. We're going to need the 3 coordinates. So we have x1, y1, x2, y2, x3, y3. That's how the input's going to come in. So we can literally just put these in 3 different coordinate variables. We'll just call them A, B, and C. So the first coordinate will just be the first 2 numbers that come in. So we'll have kb.next double. Remember, it's double precision with decimals, so we'll use next double for that. And we'll do the same for B and the same for C. So this is just getting the input of the 3 points that make up the triangle that we are circumscribing. There we go. So we have our 3 coordinates that we are circumscribing. Alright, so let's jump back to our diagram now to figure out what sort of algorithmic steps we're going to need to take to find this intersection point. So we're going to need to describe each of these perpendicular bisectors with an equation of the line. So the equation of the line you can see over here, this is point slope form, which will be really useful for our problem, because all that means is we need 1 point and the slope, and that will describe our line sufficiently. So the point that we'll be looking for is this point right here, the midpoint between A and B. We know that that point is going to be on this line. Then we also need the slope. The slope we can get from the perpendicular slope to our line segment. So to find the slope of our perpendicular bisector, we're going to first find the slope between A and B. Then we're going to take the opposite reciprocal, and that will give us the perpendicular slope, the slope that's 90 degrees to it. So the opposite reciprocal will just be the negative of 1 over the slope between A and B. And we'll do the same for this segment over here. So our goal here is to find the midpoint as well as the opposite reciprocal of the slope between A and B. So we'll use a couple helper methods to help us with that. Let's start with the midpoint. So we'll just make a static method here that will give us the midpoint in coordinate form. We'll just call it midpoint, and then we'll pass it the 2 points that make up that segment that we're trying to find the midpoint of. Now the easiest way to find the midpoint between 2 points is just to average the x's and the y's. If we just take halfway in between on the x-axis, that'll get us to the midpoint value. Same with halfway in between on the y-axis. The midpoint is the same distance to either point on both axes, like that. So we're just going to average the x's and the y's. So we'll return a new coordinate where the x, we can just do these with separate variables up here. The x is going to be the average of the two, so we'll add them up and then divide by 2. And same with the y. We'll add them up and divide by 2. And we'll just return a new coordinate that is those averages. So there we go. That's our method to find the midpoint between 2 points. So that's half of it done. Now we just need the opposite reciprocal of the slope between A and B. Now we can make this 2 steps. First, we'll just find the slope between A and B. So let's just write a method that gives us the slope, just in double precision, between 2 points. So we'll pass it just any 2 points. And we can use our good old slope formula to find the slope, just like that. So we'll take y2, we'll just make the second point be b, minus y1, and divide it by x2 minus x1. Now we will have to handle divide by 0 errors later on, but since we're going to be having to do that pretty much throughout the entirety of our program, we'll just come back to that later. For now, we'll just assume that this works in theory, and we'll come back to divide by 0 errors later. Alright, so now that we have the slope between A and B, now we just have to take the opposite reciprocal of that to get the slope of the perpendicular bisector. So we'll pass it some double, and then we'll have to take the opposite reciprocal of that. So that'll be the negative 1 over the value that we pass it. So that's the reciprocal part, and then the opposite part is the negative right there. There we go. So those are our 3 helper methods to help us find the equation of the line for both of our perpendicular bisectors. Let's just jump back up to our main method to get those written out. So for each perpendicular bisector, we're going to need a point and the slope to describe that line. So we'll just say the first line will be the line between coordinate A and coordinate B. So the slope of that line will be the opposite reciprocal of the slope between A and B, just like that. And the point on that perpendicular bisector will be the midpoint between A and B. We'll call that one mid 1. There we go. So that is the perpendicular bisector between A and B. And we'll do the same for another pair of points. Let's just do A and C. It doesn't matter which pair of points you pick. You could have done the perpendicular bisector between B and C, for example, as well. But we can just pick any 2 we want. And then we'll also need the midpoint for that. And there we go. We have a sufficient description, enough mathematical information to describe these 2 lines. All right, now comes to the major math-heavy part of this problem. We have to find the intersection point between these 2 lines that we have the equations for. So I've already just summarized the math over here. So this top equation is the equation of the line between A and B. This bottom one is the equation of the perpendicular bisector between A and C. We can solve both of those for yn. Yn in this case is our intersection point, whereas the other x and y's are the midpoints that we're using to describe those lines. If we solve both of them for the y intersection point, we can set them equal to each other right here. And that only leaves the x intersection point as a variable in our equation. So we can do some algebra to solve for xn. And this equation then, we have values for all of these numbers. So this equation here will help us find the x value of the intersection point of the two perpendicular bisectors. Once we have the x value, it's really easy to find the y value. All we do is we take the x and plug it back into one of our equations, and that'll just pump out the y. It's as simple as that. Not so simple is just putting this into code. So let's work on that now. So we're trying to find the intersection of two different lines. So this is going to return a coordinate. And then we'll have to pass in both lines. Remember, both lines are described by a slope and a point. So we'll just have the slope of the first line and the point of the first line, and same with the other one. So the slope of the second one and the point of the second one. All right, so then we'll jump over to our equation and we'll just have to copy it over. So remember, we're finding the x intersection point, and that'll be a coordinate. And that x intersection point is described by this jumble of numbers right here. So this we just have to now copy into our intersection method. All right, so I've just copied this equation here into our intersection method. That's just what this big long line is right here. And then also, instead of it returning a coordinate, remember, this is just going to give us the x value of the intersection point. To find the y value, it's just as simple as the x. All we have to do is use this equation right here. We can use either of these lines. It'll just pump out the y value of the intersection. So I'll do that. All right, so there we go. This code has been copied in from our equation of the line right here. So there we go. We have the y intersection point and the x intersection point for our intersection coordinate. So we can just return, it's as simple as returning a new coordinate given the x intersection point and the y intersection point. Fantastic. And we can implement this now into our main method. So we have our two lines. Now we want the intersection point of those two lines, or those 2 points. Yeah, the two perpendicular bisector lines. So intersection, and then we're going to pass it slope 1, midpoint 1, and slope 2, midpoint 2. There we go. All right, so now that we have our intersection point, it's time to output it. So this is going to be on a new line. So at the end of our for loop, we'll have it print a new line, but we're going to have the space separated x and y value of our intersection. Now we can use printf to format this so that there is only one decimal. If you read closely, the program wanted only one decimal point rounded off so that our output was simple enough to read. So we can do that with a format string. If you're not familiar with this, essentially each percentage block right here tells the program that, okay, I'm going to give you two arguments after this. The first one put right here and round it off to one decimal place. The second one put it right here and round it off to one decimal place, and then there's a space separating in between. So for the first one, we want the x value of our intersection point, and then for the second one, we want the y value. Just like that. So that'll output our coordinate for the intersection to one decimal place. After that, we just want to make a new line for the next test case. All right, and our program is almost done. We can just put a quick close function in here. But what we do need to consider is those divide by zero errors. So in Java, we have a double.nan for not a number values. So if you remember, vertical lines don't have a slope, or the slope is undefined. And those don't transfer well into our arithmetic operations in Java, so we're going to have to do special cases for them in each of our methods. So for example, for the slope, we need to check, do we have a vertical line? So we can do that by checking if the x-coordinates are the same. If the x-coordinates are the same, that means only the y-coordinates differ, and we have a vertical line. In that case, the slope we're going to return is undefined slope. And we can just write a quick test case as well for horizontal lines. Remember, horizontal lines have a slope of 0, so we'll return that. All right, we're also going to need some of those in each of these two as well. So for opposite reciprocal, if the slope we get passed in is 0, aka we have a horizontal line, the perpendicular line to a horizontal line is a vertical line. So we can just return a vertical slope, just like that. And the opposite is true if we have a vertical line. Now we cannot just do slope dot equals double dot nan. In Java, you're going to have to do something a little bit more special for nan numbers. They have a special method called isNaN. This is just a factor of the fact that doubles store nan a little bit differently. So we're going to have to do double dot nan is nan slope, and that will tell us if slope is a vertical line. If so, we return a horizontal line as the perpendicular slope. Alright, so that's those two done. Now we just have to handle vertical lines and horizontal lines in our intersection method. So the two cases we have here is if our horizontal line has a bad slope, or sorry, if our first line has a bad slope, a vertical slope, I guess. If our first line is a vertical slope, then that simply means that the x-coordinate for our intersection point is the x-coordinate of our vertical line. Our vertical line only has one x-coordinate possible, so that's where it's going to come from. The y-coordinate then we can get by plugging in that x-coordinate that we found into our equation of the line right here. So we're going to plug in the x-coordinate of the vertical line in for x of n, and that'll give us back the y of n, which will be our second parameter that we're putting in right here. So we're going to plug in slope times our x minus the second line's x plus the second line's y. So we'll do our second slope. Oh, and this should be 0.1, not a. There we go. So our second slope times our first point x minus our second point x. And then from there we will add our second point y. So that's just plugging it into the equation of the line. So that's if our first line is a vertical line. We also want to test if our second line is a vertical line. And there's never going to be a case where both of them are a vertical line. If that was the case, we would have parallel lines, which can never happen with non-collinear points. And you can never have a circle if you have collinear points. So our test cases will never have to handle that. So if the second line is a vertical line, well, then we'll just basically be doing the inverse of the statement above. Just replacing all these with their opposites. Like so. Alright, so our program should now sufficiently handle vertical lines as well. So let's just grab a couple test cases. Alright, now that we have some test cases, I've got about 2 here. So we'll just start off with our number of test cases. Here we go. So we're going to have 2 test cases, and then these will be our 2 test cases. So this is the result for the first one, 1, 0, which is the result that we're expecting, and then this is the result for the second one. Simple as that.